Hello everyone. Welcome to this fireside chat on the theme of networking meets cloud and edge applications. I'm Venkat Padmanabhan from Microsoft Research, and I'm here with my colleagues Zhixiong Niu and Francis Yan. Interestingly, each of us is in a different country and continent. Zhixiong is in Beijing, Francis is in Redmond, and I'm here in Bangalore. Now, coming to the theme of our discussion today, applications in the cloud and increasingly applications at the edge need to traverse a heterogeneous set of networks to get to users. And ensuring a good user experience requires applications to adapt effectively to these diverse network conditions. So the question is, how can we evaluate and test applications in a realistic manner to ensure that they are resilient to this sort of diversity in network conditions? At a high level, data-driven approaches, including machine learning, hold a lot of promise. They can help both by enabling us to create a realistic environment, network environment for testing, as well as enabling applications to adapt. Adapt effectively. In this conversation, we'll touch on a bunch of projects across Microsoft that are looking to push the frontiers on research in this sort of data-driven approach to network adaptation. Zhixiong, let me first turn to you and ask you to briefly talk about this interesting work that you and your colleagues are doing on a testbed initiative called OpenNetLab. I'm sure the audience would be quite interested in understanding what OpenNetLab is and also how it pushes the state-of-the-art compared to past work like PlanetLab and how they can get involved. Over to you, Zhixiong.
Thank you, Venkat. I think leveraging AI to boost network applications and edge computing have attracted more attention in academia and industry. Today, AI training is data-driven, and training AI models for networking and edge computing demands massive amounts of the real data with different environments. The quality of the depth of the data determines the level of AI models. Until now, the real network data are far from enough to train an ideal model for network application and edge applications. Since the Internet composed of heterogeneous access devices and the switching devices, and the transmission provide almost uncounted scenarios. To solve this issue, we are building for a new community, OpenNetLab. This is also a platform. The mission of OpenNetLab is to provide help on data-centric networking AI. It includes common benchmarking datasets or ImageNet in networking area through a distributed networking platform with many collaborative nodes for researchers to collect real networking data and training and evaluating their AI models for various networking environments, including AI in internet, cloud, wireless, and mobile networks. Compared with other solutions, for example, PlanetLab, as you know, we are more AI and data-centric. When researchers are working on OpenNetLab, we see their agreement. Actually, they are working with us to build a data set for networking AI for their own experiments and also for the whole community. So they are working on the and since they are working on the authentic third-party platform, the data are endorsed by OpenNetLab. Other guys can reproduce and experiments in the same networking configuration. We are also provide a lot of tools to boost networking AI and the networking dataset. We are located in a whole life cycle of networking AI. We provide RTC gym for bandwidth estimation, and they can train their AI model on the simulator. We also provide emulation to help them to do the emulation on their environment. Finally, we run real evaluation on OpenNetLab nodes. They can evaluate their model, even A/B testing their model before their release on the OpenNetLab. To join OpenNetLab, the researchers should sign an MOU with us, and they can use the nodes from OpenNetLab and also contribute their nodes to OpenNetLab. We also have a data-centric networking workshop on Microsoft Research Summit on October 21. Everyone is welcome to this workshop, and we will cover a lot of topics in networking AI in this area. By the way, the bandwidth estimation challenge on MMSys this year is also good showcase of OpenNetLab. After our production group and us decided to hold this bandwidth estimation challenge, we released our AlphaRTC. The AlphaRTC is based on WebRTC but supports bandwidth estimation AI models. To help the participants train their models, we also provided the AlphaRTC gym to serve as a simulator to help them train their model. It enables the participant to train and evaluate their model with simple Python scripts. So both networking experts and data scientists can join this challenge easily. I think Francis is also the committee co-chair. I think he can talk more about the challenge, the more details about the challenge. Okay, Francis.
Sure. Thanks, Zhixiong. This is Francis. Thanks for having me here. So yes, the grand challenge we organized and actually just concluded at MMSys 21 the other day was about a key algorithm in real-time video applications called bandwidth estimation. You can think of it as a congestion control mechanism for video conferencing. It observes the network conditions and outputs an estimate of the network capacity that's available in the future, which is then used to control the video codec to compress video frames into appropriate bit rates that do not exceed that available bandwidth, with the goal of improving the user's quality of experience. And this bandwidth estimation problem is sort of a natural fit for data-driven approaches, since we've seen so many heuristic or handcrafted algorithms fail to perform consistently well in the face of heterogeneous real networks. Therefore, as Zhixiong just said, we provided a simulated environment as part of the challenge for training machine learning, especially reinforcement learning or RL algorithms. And in this way, we hope to facilitate data-driven approaches. And during the challenge, we received 6 valid submissions in total, and eventually selected 2 teams as the award winners. And it's worth noting that the entire evaluation was done on OpenNetLab, because after all, real-world performance is all that matters. We certainly don't want a learning-based approach to overfit the training environment we provided. And OpenNetLab, on the other hand, features a variety of real network situations. These various types of networks turn out to be really helpful in differentiating algorithms. Some learning-based algorithms really specialize in just 1 or 2 types of networks, but consistently performing well is really difficult. And going forward, we hope OpenNetLab can serve as the testbed for such real-time video applications, since we've developed the framework that enables OpenNetLab nodes to have automated video calls with each other.
Okay, great. Thanks, Francis and Zhixiong. This is really fascinating, and congratulations on the successful competition you held. I'm sure it will just grow with time. As researchers, we always like to explore multiple approaches, right? So I think OpenNetLab is a great example of a test bed that provides realism and real-world settings for testing and evaluating applications and bandwidth estimation in particular in the context of this competition. But beyond a point, it gets hard to scale test beds and ensure coverage and so on. Now, for the longest time in the networking world, simulation and emulation have been tools of choice for evaluating protocols and applications. And these are attractive because they are relatively inexpensive. You can run them in the lab and you can do evaluation. You don't have to actually build out a huge test bed. The challenge, however, is in ensuring realism, right? How do you configure your simulator or emulator to faithfully reflect reality? And again, data can come to the rescue, right? And that's the idea behind a project called iBox, or Internet in a Box, where the idea is that when you look at an application that's running, like for example, you are presumably on a Teams call viewing this recording or viewing this session rather, and during the call, the application can gather fine-grained packet-level traces reflecting the network conditions on several different paths, right, of the participants in a call like this. And with such data, we can then use iBox to train a model of these network paths using a combination of networking domain knowledge as well as machine learning that then enables us to, not just capture basic things like, bandwidth characteristics and delay characteristics of the network, but also more involved things like cross-traffic behavior and issues like packet reordering that sometimes may happen in the network and so on, right? So there's a fair amount of complexity that can be faithfully recreated. And we've built this at iBox, and we've used this to evaluate different flavors of TCP protocol, essentially do a bake-off, and found some pretty promising results. As it turns out, Francis has been quite a pioneer in this space. So when he was a grad student at Stanford, he and his colleagues worked on a system or a testbed called Pantheon, and also created the notion of a calibrated emulator, which our projects like iBox build on, right? So Francis, maybe I can invite you again to talk us through very briefly Pantheon and what the goals were and what impact it has had.
Sure. Thanks for the kind words, Venkat. I'm so happy to see that iBox extends this line of work. And as for Pantheon, it's a real testbed that I built during PhD, and we used to have real nodes in more than 10 countries, sort of like OpenNetLab, except we focused on congestion control schemes. And we implemented a reference set of more than 15 congestion control algorithms, and also developed a software library to help people benchmark any congestion control algorithm. And maintaining a real platform like Pantheon is kind of time consuming, but I'm happy to see that the effort paid off eventually, because Pantheon ended up assisting 4 algorithms from other research groups in publishing at top conferences, including 2 NSDI papers, 1 CCOM, and 1 ICML papers.
That's great. Yeah, no, I think it's not often that someone's grad school work gets used by so many other people and so on. So I think congratulations on the project. So I want to switch gears now. I know so far we've been talking about the infrastructure, creating a network test bed or a simulator or an emulator that allows you to do realistic evaluation. But the other place where data and ML can help is in enabling applications to adapt better. In particular, using ideas like reinforcement learning for bandwidth control. So maybe again, I'll turn to you, Francis, because you're doing really exciting work here. Maybe you can talk about your work and in particular, what lessons it holds for making reinforcement learning based bandwidth control practical and make it real.
Sure. My current research agenda really focuses on creating practical machine learning or reinforcement learning algorithms, as you said, that are deployable on real network systems. So I've been thinking a lot and do have something to share in this space. And besides the bandwidth estimation challenge that we just talked about, I have another ongoing work that tackles a similar problem, but in group video call settings using reinforcement learning. And also before that, during my PhD, I had another project called Puffer, which included a practical RL algorithm for adaptive bitrate streaming, or ABR. And my algorithm was able to consistently outperform the state-of-the-art ABR algorithms on hundreds of thousands of real users. And based on my experience, the key for RL to stay practical on real systems is to achieve good generalization. And by generalization, I mean it's common for RL to achieve robust and high performance in their training environments, whether they're simulated or real environments. And generalization really focuses on transferring that good performance to the target deployment environment. So Puffer's ABR algorithm achieved generalization by training on batches of real log data from the deployment environment, which is known in the literature of RL as offline RL or batch RL. And this approach is desirable in many situations, since it's not intrusive to real systems. All it needs is log data. And since RL learns in situ on log data from the real environment, it naturally gets better generalization than training on synthetic or artificial data. And on the other hand, if your algorithm has to train in simulation, maybe because it really requires an environment to interact with during training, then now we circle back to a gap called simulation to real gap. And that's the whole reason of building calibrated emulators, because they reflect and capture the reality of the networks. And this is known as system identification in the RL literature. So, from another perspective, I have another ongoing project that's trying to close the simulation to real gap using another technique in RL called domain randomization. And the simplest version of it just randomly selects each environment parameter from a range of values and then uses these parameters to instantiate the training environment. And recently, we see a totally different perspective of achieving generalization, and that is to leverage heuristic algorithms in some way. Since heuristic algorithms tend to be understood better, they are more reliable, although they might not be optimal in many cases. So it's actually quite interesting to see that the top 2 places in our MMSys Grand Challenge have both adopted a hybrid approach that combines machine learning with heuristic approaches so that they could have the best of the 2 worlds.
Okay, that's very interesting, Francis. In fact, I do think that there's a lot of value in combining domain knowledge or domain expertise with machine learning rather than going to one extreme or the other, right? So I think looks like your results bear that out. So that's great. So I think that brings us to the end of this little session. I'd like to thank everyone for joining this session, and we hope you enjoyed it. Information like papers, data, other resources on pretty much everything that was talked about here is available online, and we invite you to take a look. And if you're interested and would like to find out more, do reach out to Francis or Zhixiong or me, and we'd be very happy to engage with you. Thank you.
Thank you, Venkat.
Thank you.